going to be looking at how we work out the pH of a base. Now we know that it's going to be above 7, so we don't have to worry about that. If you get a number less than 7, you know you've made a mistake and you have to go through the process again. The first thing to sort of consider though, to be able to do this, is to realise that water actually naturally dissociates when it reacts with itself. So when two water molecules meet, sometimes they dissociate, sometimes they just form bonding between them called hydrogen bonds. But this is what happens every now and then. It breaks up into hydronium and hydroxide. So this would be our conjugate acid, formed, let's say, from water acting as a base. So here's accepting an H+, and it's accepting that from water acting like an acid, so therefore turning into its conjugate base. Alright, so it's acting as both. So it's what we call amphiprotic. It's acting as an acid, and it's acting as a base to make the conjugate acid and the conjugate base. Well, these are actually the two ions that really matter for calculating pH, hydroxide and hydronium. But actually it's most important to look at the hydronium ion concentration. Now, pure water we should know the pH of, and we did it in our experiment at the start of this topic. And we know that the pH of water is 7.0. We should also be able to use the work that we did last time to work out what the concentration of hydronium ions would be. So I can take this and go, well, the hydronium ion concentration must equal 10 to the power of the negative pH. So 10 to the power of negative 7 moles per litre. So I actually know the concentration of this here is 10 to the power of negative 7. Because it must be if the pH is 7. 7 also means neutral. That means it's not an acid and it's not a base, which means the concentration of these two ions should be equal. If they're not equal, then it's an acid or it's a base. But if they're equal, it's neutral. This has a pH of 7.0, it is neutral. So therefore, the concentration of hydroxide ions must also be 10 to the negative 7 moles per litre. So they're the same. Now I'm going to link this to another part of the topic, equilibrium, because look, it's an equilibrium. These are tiny concentrations. This equilibrium is very much favouring the reactant side, the left-hand side, because only 10 to the negative 7 moles per litre of each of these exist. These are still going to be around about 55 to 55.5 moles per litre, huge numbers. So the equilibrium constant for this is incredibly small. So I could write the equilibrium expression for this. So I will. Now, I'm not going to put the C there because this is a special equilibrium called the water dissociation equilibrium. So it's called KW. And yes, the W is for water. We're being quite commonsensical here. Okay? So KW is going to be the reactants over the products. Well, actually, the product reactant concentration doesn't change a lot, so we don't include it in this particular one. It's also pure water. You never put pure water liquid. You never put liquid water in a K expression. So the equilibrium expression is going to be this, which means if we know these two values, we can plug those in and solve. 10 to the power of negative 7 times 10 to the power of negative 7. Now you guys should know enough about exponents and how to work with them to know what the answer is to that, I hope. If they're exponents, we add the exponents, so the answer is 10 to the power of negative 14. Now, someone, sometime, probably in the last 3 years, told you what the pH scale goes up to. 14. They lied, by the way. It goes beyond that. But let's say, okay, that's correct enough. That's why we said it goes to 14. For the things you deal with in class, 0 to 14 is a realistic scale for you to work with. Okay? Now, knowing this equation, which I'm going to put a pretty little bubble around because it's so important, and you're not given it, by the way, you have to remember it. Knowing this will help us work out the pH of a base. So let's say, for argument's sake, I had 0.01 moles per litre. Sorry, I'm going to give one more significant figure there so that my pH can be more precise. 0.010 moles per litre of sodium hydroxide. Now, sodium hydroxide has only one OH in it. Okay? So therefore, this will make 0.010 moles per litre of, of hydroxide ions. So that means I know the number that goes in here. I know this number because it never changes. It's 10 to the negative 14. So the unknown is the hydronium. So what I do is I like turning this one into a little triangle, like I do with my NMM equations and stuff like that, where I have hydronium and hydroxide on the bottom, and I've got Kw, or 10 to the negative 14 is what I usually put in there, 10 to the negative 14 in there. Then I hide what I'm trying to find. Well, I'm always trying to find hydronium because I want to find pH. That's my ultimate goal. So if I know that I want to try to find that, it's Kw divided by hydroxide. So let's do that. (10 to the negative 14 over 0.010, which is two places away from decimal point. So it's 10 to the negative 2. Because I like doing it this way because, you know, remember I said I liked logs? This is why I like logs and exponents. I know that divided by is the same as minus when I look at my exponents. So this is going to be 10 to the negative 12 moles per litre. Negative 14 minus negative 2 is negative 12. I also know that pH is 10 to the negative, pH is negative log of this number here. And if I put that into my calculator, I get that the pH equals 12. So actually working out pH of a base isn't too hard. It's bigger than 7, so I know I'm pretty confident that I've got it right. Okay, I'm pretty confident because it's bigger than 7. They're not always this easy though. What if we had something that had 2 hydroxides in it, like calcium hydroxide? That's also a base. This year we assumed that it completely dissociates. It's not strictly true, just like with the acids, not strictly giving both of their hydrogens to water for, say, sulfuric acid or phosphoric. It's a little bit more complicated when you have 2 hydroxides or 3 hydroxides as well. But this year you assume that it does. Okay, so if that was the case, this wouldn't be, I'll do it in a different colour. Let's say it was calcium hydroxide. Now in reality, you wouldn't get a concentration this strong of calcium hydroxide. I think it would be a precipitate, but let's say we would. Because each of these has got 2 hydroxides, the concentration of hydroxide ions is not 0.01, but is 0.02. So you'd have 0.02. That capital M just means the same as moles per litre. It's just shorthand. Moles per litre hydroxide. So therefore, you'd have to do the equation a little bit differently. Hydronium ion equals 10 to the negative 14 over 0.020. And that'll give you a value that's still a little bit different to that. My brain's quickly trying to work it out and struggling. I think it's 5 times 10 to the negative 11, but can someone with a calculator quickly check that, please? I'll put it down and hope that I'm right. Is that right? The negative 11?
12.
Is it 12? Cool. Okay, and moles per litre again. Okay, and then if I do negative log of that answer, so negative log of 5 exponent negative 12, I'm not going to get a pH of 12, I'm going to get a slightly higher pH. So again, someone with a calculator can do it for me very quickly. 12.3. Okay? So just a slightly higher. You can see even though it's got twice the concentration of hydroxides, it's not a way higher pH. It's got from 12.0 to 12.3. So that's really all you need to be able to do with your calculations. If you can work out the pH of an acid, fantastic. If you can do it with the one that's got more than one H plus ion in it, that's even better. Then, if you get given a base, again you look how many hydroxides it'll make. You plug that number in to this triangle here, knowing Kw, and that will help you find hydronium ions. You then use the hydronium ions to work out the pH. So it's got an extra step in it. Right? And that's what makes these worth merit rather than just achieved. Okay, because it's just that extra step in them. Okay.